In this video, I want to talk about something specific to statistics. I'm calling this independence in sampling. And I'm going to assume that you're already familiar with independence and conditional probability and probabilities. So if you haven't already watched the conditional and probabilities videos, you should watch those first. So I have an example here. In a survey of 987 adults, 482 of them said they had at least one dog. So if we select 3 adults from this sample, what's the probability that all 3 have dogs? So hopefully you can recognize that this is going to be an and probability. So for an and probability, we're expecting to do multiplication between the probabilities. But the other thing that we need to know is whether these 3 events are independent or not. Well, when you select 3 adults from this group of people, in most cases, if it doesn't specify, that means these are 3 different adults, which means once we've picked the first person, we're not going to pick that person again. This means that we're selecting the adults without replacement. And if we don't have replacement, then that means that these events are not independent. So in this case, the probability that the first person has a dog, we could just say, well, there were 482 people with dogs out of the total of 987. That's the probability of finding somebody with a dog. But if we're not replacing, then when we go to the second person, the probability that they have a dog, well, there are only 481 people that have dogs left. We've already taken one out, since we have to assume that the first person has a dog. The total also goes down, so 986. And when we get to the third person having a dog, again, we have to assume that the first person has a dog and the second person has a dog. This is that conditional probability. So now there are only 480 left out of 985. So the probability of each of these is slightly different because we're sort of removing each adult out of the pool as we go. You can imagine if you selected a lot of people, eventually we would actually run out of people with dogs. So, for example, the probability of selecting 500 people that have dogs, well, that's impossible because there were only 482. So in the extreme cases, you can see where this would make a big difference. Rounding to 4 decimal places, we get a probability of about 11% here. Now, what if we were selecting 25 people? So the process would be the same. We would say that the first person, the probability of them having a dog would be 482 out of 987. Then the second person, we said 481 out of 986, 480 out of 985, and we'd have to just keep on doing this 25 times, and so on. Well, this is going to be terrible. So when we have a large group of people that we're selecting in this kind of manner, we run into sort of computational problems. Now, could we do this? Sure. You might end up overloading your calculator, but we could compute this. For simplicity's sake in the statistics class, though, we're going to use a 5% guideline for independence. And what this guideline says is that when your sample is less than 5% of the population, so you're picking a group of people that's relatively small, you can treat these selections as being independent even though they usually aren't, right? Even though we're pulling out without replacement, we can just assume that since the probability is changing by so little, right, the difference between, for example, 482 out of 987 and 481 out of 986 is very small. So in these cases where our group is small enough, we don't have to worry about affecting the probability every time. We can just assume independence. So for this one with 25 people we were discussing, I'd say, okay, 25, what percentage is that out of the total number of people we're looking at, or out of the pool? In this case, this is about 2.5%. So since this is less than 5%, we can say, all right, 25 people is small enough that we don't have to worry about the effect of removing each one at a time. So in this case, when we do the probability that all 25 have dogs, we can just say, all right, we're going to have 482 out of 987 times, and these are all going to be the same. We don't have to worry about changing it each time. Now we don't really want to write all this out, right, because there's 25 of these. So this is 482 out of 987 raised to the 25th, right, multiplied by itself 25 times. Be careful when you're entering this into your calculator. If you don't put parentheses around the fraction, that 25th power will only go on the 987, and you might be ending up with the wrong answer. So I'm telling it to compute this fraction and then take that entire quantity and raise it to the 25th power. Another thing that we'll see happening here is that the answer we're getting, this is actually scientific notation. So 1.6529, etc. The capital E there means times 10 to the negative 8th. So if you remember your scientific notation, a negative power means that our decimal place has to move to the left, in this case 8 times. So our answer here would be we'd have to have 7 zeros, 16529. This is an incredibly small probability that if we picked 25 people, all of them would have dogs. We would not expect this to happen. All right, so here's one for you to try. Make sure that you're thinking about, are these events independent? And if not, are we allowed to assume they're independent, right? Does it satisfy that 5% rule? That's it for this video. See you next time.